So this course is aimed at people who have anything to do with hazardous areas in the design, the selection of electrical equipment, the manufacturing of that electrical equipment that is to be used in the hazardous area, anybody involved in installation in the hazardous area, operating the plant in the hazardous area, maintaining the electrical equipment in the hazardous areas, and a little bit about troubleshooting and repair as far as making sure you meet the requirements of the hazardous area installation requirements and maintenance, and doing it safely. This course only looks at the electrical equipment. There is move within the IEC EX community to introduce mechanical equipment into the certification requirements as well. Before I move on, has anybody got any questions? Okay, I'll move on. Now, I'm sure we all know what an explosion looks like. Hopefully we haven't experienced any of these firsthand at our workplace. I've got some of the best jobs in the world. I actually get paid for blowing things up. It's fantastic, and therefore as a result I'm probably going slightly deaf, but I see a lot of these explosions. Some of them are very spectacular, and some of them are a lot bigger than what we anticipate. But there's some definition of what an explosion is and some examples. Throughout this presentation we'll only be talking about explosions due to electrical equipment in flammable or potentially flammable atmospheres. I suppose we need to define what the hazards are. We have two basic types of hazards: natural hazards and man-made hazards. Natural hazards such as blizzards, floods, earthquakes, heat waves, hurricanes, tornadoes, tsunamis, volcanic eruptions, all of which seem to be happening with alarming regularity these days. We can't do too much about those. We can try and design our buildings and build levees and other sort of man-made features to try and minimise the damage, but we can't do much to actually stop these hazards occurring. There's all sorts of man-made hazards that we introduce into our working environment, and we'll be concentrating mainly in the use of the hazards as far as the use of flammable gases and dusts are concerned. Most dusts are in fact incendiary. They will burn or they will blow up or will explode if given sufficient energy or enough heat. So even sugar, corn flour and normal household dusts will combust given the right environment. So we're going to be looking at trying to contain to an absolute minimum the risk of the explosion or fire occurring due to the release of a potentially hazardous area. Okay, so we've decided that we've probably got a hazardous area, but in order for an ignition to occur or burning to take place, we need three components. We need oxygen. Now, oxygen is available in air. Air contains 20.9% of oxygen. We also need the hazard itself, the fuel, the dust, the vapor, in sufficient quantities to become dangerous. And of course we also need a source of ignition. Now these three components are known to make up the fire triangle. If we remove any one of these elements, then we haven't got a hazard. We haven't got a risk of an explosion. The question is, how can we remove some of these hazards? So I'm just going to go back to explain this. All the protection techniques that we're going to look at for protecting the electrical equipment removes at least one of these components of the fire triangle. with the exception of one of the protection techniques. One of the protection techniques permits all three components of this fire triangle to be present. And as such, it's really important that we ensure that that type of protection concept is installed correctly, and perhaps more importantly, once it is installed correctly, that it's maintained so it doesn't degrade and allow the explosion to transmit. More about that though in details later. Has anybody got any questions so far? Excellent. Well, that either means that you're all understanding it, or you're completely bamboozled by my Yorkshire accent. The first step we need to do, if we've decided that we need to identify if we actually have a risk of an explosive atmosphere being present. Clearly, I'm sure we all appreciate that if we're dealing with petrochemicals, then somewhere along the line we are going to have a potentially explosive atmosphere dealing with petroleum. What we may not realise is if we're dealing with certain dusts, such as sugar, corn flour, etc., under certain circumstances, that can also become an explosive risk. So what we need to do is have a think and see if we can identify any explosive hazards that we may have in our workplace. Or better still, perhaps we need to get some people who can identify these risks for us so we don't become too liable. Once we have accepted the fact that we have got a potentially explosive atmosphere, then the best thing to do is to remove all the electrical equipment, and I'm going to extend the scope of this a little bit, not only the electrical equipment but any potential igniting sources away from this hazardous area. If we can do that, then we don't have to purchase suitably certified electrical equipment to put in the hazardous area, and we don't have to pay for the additional labour costs associated with ensuring that we maintain the equipment in accordance with the maintenance standards. So it becomes a lot cheaper. Certified equipment you pay a premium for, and you're also going to be maintaining it and keeping records on a regular basis. So if we can get the electrical equipment out of the hazardous area, it's best for the bean counters, sorry, the financial people, and it's also a safer method of working. However, in a lot of situations, we can't eliminate the electrical equipment from the hazardous area. We need that electrical equipment to either control the hazardous area or provide measurements. So if we're stuck with having this electrical equipment in the hazardous area, we need to make sure that that equipment is suitable for that risk. And each potentially explosive atmosphere has several different characteristics. Some of it can be easily ignited by a hot surface. All the gases have different auto-ignition temperatures, and a lot of them have different ignition temperatures, have different ignition energies. So we need to make sure that the equipment we purchase and install is suitable for our particular hazard. We've also got to consider the risks of the electrical equipment either malfunctioning or being operated beyond its normal manufacturer's rating. So of course, the ignition also needs to be coincident with the presence of the explosive atmosphere being present at the time. So there's a degree of risk assessment as to the probability that the gas is there, and we'll be looking at that when we look at area classification. An important one, and it's one that's probably fairly commonly overlooked, especially perhaps here in Australia, is the certification to acceptable standards. What standards are acceptable? What certificates are acceptable within Australia? Just because something is certified doesn't mean to say that it's suitable for use in our environment. Here in Australia, we do not accept ATEX. ATEX is a mandatory requirement in Europe, so they have to have ATEX certification. Here in Australia, we only accept IEC EX certificates, Aussie X certificates, and ANZ EX certificates. We don't accept ATEX because ATEX is a European trading directive and Australia isn't part of Europe. Likewise, in America, they are likely just to be able to accept UL listed equipment or FM listed equipment. Also, the certification, even if we've got an appropriate certificate to an accepted standard, we need to make sure that equipment is appropriate to the apparatus group and the temperature classification, and we are using the equipment within the specified limiting conditions, such as the ambient temperature that it's been designed for and the normal atmospheric pressures and oxygen concentrations. Any questions so far? Okay, so in order to ensure the overall plant safety, we need to take a systematic approach to determine how we're going to achieve this. First of all, we need to identify the process and what hazardous areas our process generates, what are the chemicals involved, what is the ignition temperatures, what are the overall ambient temperatures that we're dealing with, the plant pressures, the apparatus group of the gas itself, and that just forms our working background. We then need to have knowledge of the actual process. Once we've got the process identified, then that will help determine where the potentially explosive atmospheres are. Okay, Alexei, I'll just finish this slide and then come back to your question. So once we've got the process sorted, that will allow us to identify where the potential hazards are. We know if we've got a process vessel where we're storing the, shall we say, the petrochemical, then obviously inside that tank itself is highly likely to have the hazard there all the time. In the pipes that are feeding it, then they are likely to be there all the time as well. In the overflow pipes, then perhaps we wouldn't expect the hazard to be there all the time. It could be there frequently or rarely. Outside the plant, outside the piping, etc., then we may well say we wouldn't be expecting the hazard to be there all the time. So a degree of risk assessment has gone into the process already there. Once we've worked out where the potential hazards are, then we need to try and keep all our electrical equipment and other potential ignition sources out of that area. And we try and minimise the electrical equipment in those areas. If we can't, then we need to select the appropriate protection technique for the equipment and that zone, that area classification. Now, Alexei has asked a question. Could you repeat about the American approvals? Okay, the American approvals, in order to use equipment inside North America, then you would need to have equipment that is certified or accepted by United Laboratories or certified by Factory Mutual. I believe they are the only bodies that they recognise for the surface industries. If you're wanting to use your equipment in underground coal mines in North America, then you need to approach MSHA. And they will have different standards than the rest of the world. The rest of the world standards are very closely aligned. We all follow the IEC EX process, and some of the countries have slightly different variants of those standards. However, the Americans tend to stick to their own standards, and these are quite often significantly different to the IEC standards. One of the main reasons we have this difference is the rest of the world works on the metric system, where North America still have the imperial feet in inches system. So it makes it quite difficult to try and get a consistency throughout the whole world, including North America. Countries in South America will probably adopt the IEC standards or variants thereof. Now, does that answer your question, Alexei? I'll pause for a few moments to give you a chance to advise me whether that addresses your problem, and also gives other people opportunity to ask questions as well. Okay, nobody's asking questions. Can I just ask people to either put a smiley face just to make sure that I'm not talking to myself? Okay, Ross can hear me. David can hear me. Alex, you can hear me. Okay, so can I assume then that nobody's got any questions? Okay, excellent, thank you very much. Ross, I'll move on. If you have got any questions, then feel free to either ask them as we're going along. At the end of the presentation, I'll stay online for 5 or so minutes, and if anybody wants to ask me any questions, then I'm more than happy to answer. Okay, the first hazardous areas really that were developed was as a result of the mining industry. The mining industry, coal mining industry that was, produces methane, and methane is an explosive gas, and quite a lot of incidents occurred during the coal mining industries. First of all, in the olden days, all the mining was done by hand, and the relatively small pockets of methane were given off. In the olden days, what they used to do, first thing in the morning before they start work, they used to send the apprentice in with a lighted taper on a 10-foot pole to go down the mine and light all the pockets of methane to make sure all the gas had burnt off before the rest of the workforce went in to dig the coal out. This obviously wasn't a good career move, and several people lost their life doing this. One of the latest developments that really improved the safety of people in the mine was the Sir Humphrey Davy lamp that was invented in 1816 by Sir Humphrey Davy. And this basically, even though it was a naked flame being used underground, was protected by what we would these days call a flame-proof enclosure. Now, these flame-proof enclosures actually contain the flame, and the way the flame actually reacted with the gas, a lot of the experienced miners could actually tell the level of methane by the way the flame behaved. I left the UK in 1997, and in the underground coal mines in UK, the Humphrey Davy lamps were still officially certified to be used underground. And a lot of the experienced miners found they were a lot more reliable as a means of gas detection by keeping an eye on the flame than the modern, at that stage, modern gas detectors at that time.